Welcome to this explainer. You know, every single time you pull out your phone to check a map, you're actually looking at one of the oldest, most fascinating translations in human history. We're talking about how cartographers take our massive, uneven, completely three-dimensional world and somehow flatten it onto a two-dimensional screen. Okay, let's dive right into this.
So here's the central mapping problem we're going to solve today. How exactly do you fit a three-dimensional mountain onto a completely flat screen? And more importantly, how do you do it without losing mathematical accuracy while still making it make sense to the human eye? Well, the answers lie in a very specific set of tools. Here is our system initialization, basically the data layers we're going to decode today. We'll start with the 3D mapping problem, then move on to ground plans, elevation models, contour lines, colors and shading, and finally, the terrain skeleton.
Section 1, the 3D mapping problem and how we reduce complexity. Think about our environment for a second. It's a continuous, totally uneven surface, packed with mountains, valleys, plains, you name it. Cartographic modeling is an essential translation process here because we absolutely cannot, and frankly, we wouldn't even want to, capture every single chaotic detail of reality. It would just be noise. We have to reduce that complexity to actually communicate the information effectively. Moving on to Section 2, ground plans and situation, specifically focusing on orthogonal projection. To render a 2D footprint, which cartographers refer to as the situation, we use something called orthogonal projection. Imagine taking points scattered across a bumpy terrain and projecting them straight down at perfect right angles onto a completely flat map plane below. The crucial thing to understand here is that this mathematical projection ensures that horizontal distances between points keep a constant scale on the map. This is absolutely vital for accurate measurement, so you know exactly how far you're actually going to have to walk.
And it's fascinating to see how that scale is practically applied to real-world objects. Take the official drawing regulations for a German 1 to 25,000 scale map. A massive federal highway is graphically encoded with a specific scaled line width of exactly 1.82 millimeters. That tiny line corresponds to 45.5 meters in the real world. A single-track railway? That gets just a 0.40 millimeter line. By doing this, cartographers systematically simplify a wildly complex reality into a clean, readable code.
Up next is Section 3, Digital Elevation Models Explained, where we start mapping the third dimension.
So, to map that third dimension, we need raw elevation code, but you really have to know what it is you're measuring. We generally distinguish between two primary models. First, we have a digital terrain model, or DTM. Think of this as an X-ray view. It describes just the bare relief surface, the solid earth or water, nothing else. Then, on the other hand, we have a digital surface model, or DSM. This acts kind of like a digital blanket thrown over the entire world. It captures the highest points of absolutely everything sitting on top of the Earth, like buildings, bridges, and trees.
Which brings us to Section 4, the power of contour lines and how we slice elevation. Contour lines are just an ingenious method of connecting points of identical height. Imagine a 3D mountain profile being mathematically sliced into flat horizontal planes. When you project those slices down to a 2D plane, you get your contour lines. The immediate takeaway for anyone reading the map is super simple. The closer those lines are clustered together, the steeper the terrain. Now, the gap between those slices isn't random, it's highly calculated. Cartographers call this equidistance, the constant vertical height difference between neighboring contour planes. But how do you choose that specific distance? Well, there's a solid rule of thumb. The equidistance should be at least 3 to 5 times your baseline elevation accuracy. This basically ensures the map doesn't accidentally suggest a level of precision that the raw data simply doesn't have.
And for the math lovers tuning in, there's actually a specific equation for this, called the Imshoff formula. Cartographers use this to calculate the absolute optimal contour spacing based on the map's scale. It ensures that whether you're mapping a totally flat plane or a crazy jagged mountain range, the lines remain perfectly readable to the human eye without just blurring into a solid block of ink. To keep that readability top-notch, the contour line system is broken down into a structured data readout. You don't just use one type of line for everything. We have main contours for the standard intervals. Then we add in index contours. These are emphasized, thicker lines, drawn maybe every 50 meters, and they act as visual anchors. Finally, half contours are dashed lines layered in to capture really subtle local forms that might otherwise be completely missed.
When you see this system in action, it's pretty brilliant.
Those thicker index contours at 50 meters give your brain an immediate height reference. Then, tucked right in between the main lines, the dashed half contours at, say, 35 and 65 meters pull out these subtle little bumps in the terrain that a rigid 10-meter interval would have totally smoothed over. It just massively upgrades the map's overall readability.
Let's move to Section 5, Colors in Shaded Relief, or Visualizing 3D Illusions.
One really powerful technique here is the use of hypsymmetric layers. This involves discrete color tints filling the spaces between elevation intervals, giving your brain an instant qualitative impression of how high the terrain is. But when you overlay contour lines onto those colors, boom, you suddenly have a map that offers both a quick visual impression and strict quantitative measurement. If you've ever used a physical terrain map or a hiking GPS, you've relied on this exact combination.
But to really trick our eyes into seeing true 3D depth, we activate shaded relief, specifically oblique light shading. The map actually simulates a light source, usually shining from the top left, which casts realistic shadows across the terrain. Combining this shadow effect with transparent hypsymmetric layers and contour lines creates a stunning, almost tactile representation of the mountains. What's truly amazing is that those shadows aren't just artistic guesses from the mapmaker. They are pure math. Behind the scenes, mapping software uses complex geometry to calculate the exact reflection intensity for every single microscopic terrain cell. By computing the angle of the simulated light against the slope and orientation of the digital terrain, it calculates an ideal Lamberton reflection. That essentially means it figures out exactly how light scatters off a matte surface to make those digital shadows perfectly realistic.
Finally, Section 6, Mapping the Terrain Skeleton, the Structural Framework.
The terrain skeleton is built out of skeleton lines and fall lines, which describe characteristic changes in slope. They trace the very highest points, like ridge and crest lines, as well as the lowest points, like the valley lines where water flows. Even if you were to completely erase all the contours and colors from a map, these skeleton lines would still clearly show you the fundamental structural backbone of the environment.
Now, before our sleek digital overlays and mathematically calculated shadows came along, cartographers had to map the skeleton entirely by hand using something called hatchers. They painstakingly drew these dense lines down the slopes. Using systems like the Lehman scale, the rule was the steeper the slope, the thicker and closer the lines were drawn. So a 30-degree slope meant heavily blacked out areas. It was absolutely an incredible feat of drawing, but it often resulted in very dark, incredibly complex maps that could actually be quite hard to read. So, when we put all this together, we get the complete topographic code. Digital terrain and surface models provide the raw data. Ground plans lock down the 2D objects using orthogonal projection. Contour lines and specific spot heights mathematically slice and pinpoint the elevation. Hypsymmetric tints and calculated shadows render a stunning 3D illusion. And finally, skeleton lines ensure the structural form is perfectly maintained. Layer by layer, a completely flat screen tricks your brain into navigating a deep 3D world.
Which leaves us with a massive question for the future of geospatial data. Today, we've decoded the brilliant workarounds cartographers use to translate 3D terrain into 2D space. But as AI-driven, fully interactive 3D digital twins and augmented reality become the new standard, will these traditional cartographic translation techniques, the contours, the mathematical shading, the flat map itself, eventually become entirely obsolete? It's definitely something to think about the next time you open a mapping app on your phone. Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.